Thank you. Welcome to the talk highlighting the OCP white paper, which we focused on challenges and solutions on the chiplet interconnects and SIP testing. I'm Rajesh Pendurkar, and I'm currently working at Capgemini, and part of this paper is presented by Aparna, who is at Synopsys. We'd like to acknowledge the co-authors of this paper from various industries. And this work was done in collaboration under Open Chiplet Economy, a subgroup of the OCP. So this is the outline of the talk. Actually, the white paper is very comprehensive. So we try to have a succinct summary of the main topics covered in this paper, which is a brief outline shown here. So let's focus on the problem statement, right? So as segments such as consumer, automotive, high-performance computing, especially AI, ML applications are exploded, the need for multi-die designs are growing. So this growth is also complemented by the constant pressure of reducing the time to market, and that is not going anywhere. So this makes testing of the chiplet-based system and package a very challenging problem. Three important challenges. First is getting the known good die, and if you have been in this industry for a while, it's not new. Known good die has been discussed right from the days of MCM, multi-chip modules. Of course, everywhere you are building a product hierarchically, we need to have a guarantee the defect-free dies before you assemble them using advanced packaging, especially heterogeneous integration these days. Even a standard packaging, it is the same story. Second, the robust design for testability architecture. It's actually a must, especially covering the hierarchical aspects for structural testing at each level of integration, from chiplets all the way to systems. So that will definitely need to guarantee that we have a known good stack. And thirdly, chiplet level test, both structural and at this time we are also going for a functional test. They are used for guaranteeing that the interconnections between the chiplets are good after the assembly, and they can be repaired too. And these days, we have to support repair in case of failures, especially in the use case scenarios. So the test methodologies need to be in place to improve and the production test, and the need to be standardized to improve the efficiency and the quality, and to reduce the test cost, which is directly proportional to the test time. So here is an example showing one a package built using heterogeneous integration. We have seen, you can see the interposer, different dies coming from our different vendors. As you can see, the fundamental parameters of testability is what? Controllability and observability, right? And you can see how increasingly difficult from this picture, especially showing this micro balls, micro bumps, which are very small in size and pitch, compared to the bumps that actually can be accessed on the wafer level testing. In addition, sometimes you need to add also sacrificial pads, because that increases the controllability. In addition, you can see the through silicon vias in this picture, and they can also be having some defects, especially when you are assembling the package in using advanced packaging. So these defects leading to the faults, basically they lead to the functional errors. So that's the whole idea of focus of this paper. This actually covers the status that some of the chiplet test vendors have actually implemented. So we have to build on what has been done earlier. There are very good examples. IEEE has already assembled this, understood this problem and came out with the 1838 standard, which is for making the testable three-dimensional stacks. So once it is integrated with the already popular 1149.1, which is the boundary scan standard, which is the most popular and widely accepted test standard to do internal test as well as the chips, inter-chip at the board level testing. So this has been done. Another thing is you need to also have scan is also well known to have a slow access because of the way you use it from the automatic test equipment. So the proposed use of increasing the test speed using UCI or PCI protocols, which you can actually compact the test data into those protocols and reduce the test time, basically reducing the test cost. That is one aspect. Similarly, you can also use high-speed I/O. Finally, the example also shows the DFT logic here. Basically, in the interposer, actually integrated so that we can have a test controller embedded inside the interposer, and from the package I/Os which are at the bottom, we can individually access the 3 chiplets which are shown. So this has been an example. For example, this local memory, you can run the logic BIST, which is for logic test. You can get a signature out of it. So this actually reduces the controllability and observability problem from the automatic test equipment. Now, logic and memory tests, which are actually integral part of any silicon chip, need to be done through 1149.x, and when I taught X, this standard has been extended to not only integrate the structural test for digital, but also for analog, is 1149.6, and also increasing the test access speed using 1149.10. So intra-die test, it guarantees the full coverage. That is the first picture. You can have memories, then we'll have to have dedicated memory built-in self-test structures. All those can be triggered using the this standard. So we get all the tests done at internal to the chip, guaranteeing the known good die. Secondly, we need to have in a 3D vertical directions when you are integrated into advanced package, you need to make sure that the interconnection between the stack going in a vertical direction are intact, especially going to TSVs through silicon vias. So this is a second picture showing inter-die test. And finally, we also need to make sure that package level test is also done. And that actually can be possible by external test controller, which is called service processor, can trigger, which is on the third picture, making sure that your package is correctly talking to the board level. So these design for testability techniques are of paramount importance. However, the purpose of the paper is to go and solve not just current problem, but anticipated problem in the future, especially with your having such a 3D structures and reduced pitches. So this is one example of 2.5D structure showing the path where you can have an interconnection between left die and a right die. It can have a short or open, and with this existing standard, with both the chips having same standard implemented, you can check the interconnection test between left die and right die. And the upper picture is showing the current state of the art, which the test companies are adding, how to basically packetize the test data to increase the test speed with these mechanisms. And the right picture, which is another standard called 1687, is for embedded. Because a lot of times the dies and chiplets, they need to do a lot of internal monitoring of power drooping, voltage monitoring, process monitoring. So these are very important to get the yield up. So this kind of standard 1687 is very easily accessible through existing JTAG protocol, which is 11.14.1. To piggyback on what the same picture, but in the 3-dimensional, you can always just send the test data up the topmost die, because basically the lowermost die is what is talking to the outside world through the printed circuit board with these balls. But we need to check the interconnection between die 2 and die 3, and there can be a problem. So this has been implemented in companies like AMD, Intel, and they have published papers. So what this paper does is we can do another example implementation of algorithms in the vertical direction, send the test data up, and get the test data down for evaluation. And of course, this can be done in parallel depending upon your power profile. So what I'm explaining what the structural test, but at the same time, when you are bringing up the chip, we do need to focus on functional. So I let Aparna talk on functional test.
Thanks, Rajesh. So system-level tests these days mainly focus on manufacturing defect-related tests, and they do include functional tests in the test plan, but they do not really reflect the use case environment. So the tests have a methodology depicted in the paper where one-time characterizations for power, performance, and electrical validation of interfaces is necessary inside the use case environment, as well as it's important to have functional tests that reflect the use case payload, such as could also be included, pre-silicon validation payload to test the functional features inside the design. System level packages, so system level testing is also used in high volume manufacturing. So it's important to, when we go from monolithic devices to multi-die chiplets, it's important to have a lot of parallel testing involved, so that, as testing time increases, you have to have some optimization with related to test cost and test time reduction. Part of a node testing is also a huge known good die testing, as well as assembly yield recovery has always been a huge part of semiconductor manufacturing. And even if we have a very good known die, assembly can lead to defects inside the package. And when we go to multi-die systems, these systems rely very heavily on the die-to-die interconnect that goes between them. And specifications like UCIe are defining test and repair mechanisms where, in case of advanced packages which use micro bumps and can see more probability of failures than standard packages, there are redundant pins provided in the PHY where any of the links, if there is broken, the communication can still be rerouted through the redundant pins that are provided, and there is no loss in communication between the die-to-die connectivity. In case of standard packages, UCIe also specifies a degraded mode where the bandwidth in the link can be reduced if some of the links are found to be faulty. With so many features to test, also different combination of chiplets that can be tested in a multi-die system, the test cost can be huge with respect to what all needs to be done. And test cost reduction can be achieved by limiting the test time, where techniques like e-test patterns that are compressed and sent over the SSN buses at a very high speed can be made useful to reduce the test time. It is very important in multi-die systems to, of course, in all type of systems, to try to model the cost analysis that is required for the whole testing and packaging and assembly related with the package. And the expenses that are linked to conventional monolithic devices show a very linear trend on when we go from fabrication to packaging to assembly, while when we go to multi-die systems, these show an exponential trend going from fabrication, packaging, and assembly. The paper does talk about some techniques where, by shifting focus to early on and later stages of the manufacturing cycle, how economic feasibility of the package can be achieved. Over to Rajesh for more on test standards.
So, as you can expect, right, the monolithic ICs have definitely a deterministic cost profile, and as you can expect, the chiplet cost model will explode as you keep on building bigger and bigger system on a chip. However, in the long term, if you take the yield equation into account, long term you do come out with positive when you go for a chiplet cost model. I would definitely recommend you to refer to our white paper when it gets published. It will give you more detailed explanation on this. So finally, but not the least, a lot of earlier panelists have also talked about interoperability. And it's exactly also the same problem in our this problem, test standards. When you are talking about these 3-4 standards which have been used over a period and they have been mature, however, there needs to be a new thinking when you are going in third dimension, right? So that's why actually IEEE came out with 1838. But as and when we are building some new chiplet suite at smaller and smaller pitches with more bigger and bigger interfaces, the problem of failures are increasing, the probability of failures is increasing. So to get the yield up, we need to have interconnect test, and that's the whole purpose. This we had to focus our effort on coming out with this white paper. And to build upon that, IEEE as an initiative we has recently started, which I'm sort of actively participating in, is standard for chiplet interconnect test and repair. So you cannot just be satisfied with 1 or 2 nets shorted or opens. We need to take in a bigger scenario how much redundancy you can add. So this is one aspect of interoperability, and that is also been very well debated and discussed in the paper. In conclusion, this has taken a sort of a fresh look in the chiplet-based system in a package, especially in heterogeneous integration scenario, how existing DFT methodologies can be used in an effective way, as well as new innovations can be involved and integrated. For example, to address the yield recovery, test cost reduction, and how we can basically leverage the standards and build the new standards. So on this, once we concluded this effort, we also are trying to think about this as a new work stream under open chiplet economy. So you are feel free to join. That's a call to action. And that actually finishes our talk.
Thank you,
Thank you.
Rajesh.
Thank you.
Yes, sorry, I think I missed it, but do you have the white paper complete, and is it available?
White paper is under review right now and will be published. We'll send out the link when it is available on the OCP contributions website.
All right, thank you.
I have a question. It's my pet peeve about known good die, and you need probe to be able to produce it, but today we can't probe the micro bumps. So there's this concept of sacrificial pads. How do you see probe technology actually at some point trying to keep up with micro bumps getting smaller in diameter and the pitch reducing, but no ability to test them?
Actually, you have touched a very important point. Traditionally, that's why the DFT actually techniques evolved. The way ATE technologies has evolved and process technologies, I mean our silicon implementation technology has evolved. There's a big gap. And that is up to, like, for example, Teradyne, Advantage, these are the main test companies. Finally, it is the pin electronics, they cannot be it cannot be inside, right? That's the whole idea of built-in self-test. Outside pin electronics, which is required to go the probes, is not going to be sustainably keeping pace with the process. So the whole work group in this is thinking about the built-in self-test is the way to go. And I think that's even the P3405, they are trying to first now connect, come out with the language for interconnect language. So once you develop that language, you can go and program from outside and do everything inside. That's
I
one
see.
way to
So minimum number of pins needed for
Yes,
any kind
yes.
of probe.
Yeah,
And
low point count testing, because it is basically at microprobes pitch. Why I know the understanding, because it's faster, the RC is very low, so that's why it is not going to go away. Micro bumps are the way to integrate more. So I think, as I showed you in one of the picture, 3D, the only way we can do it by internally connecting those test patterns, scan it inside and test it. It will take some time, but
yeah, so don't depend on the probe companies.
I mean that I'm not a ATE background fully, but definitely R&D is going on in their side, but size kind of the probe card, if you get a chip like a 40 millimeter chip, which comes, it directly goes in the flex tester, there's no way to access, because first of all, power and ground pins are taking so many of your time. So test pins accessibility also. That's actually, we are also working on the CDX work stream, how to make it deterministic language. So actually, David is here. Okay. So he's also, that's one very good innovation is happening in another paper.
Perfect. Thank you, both of you. Appreciate
Thank you very
your
much.
presentation.